Presented by Caltech.
My name is Leonard Schulman. I'm a professor of computer science here. It's really my great pleasure to introduce tonight's speaker, Chris Umans. Chris received his undergraduate education at Williams College in Massachusetts, and he went on to earn his PhD at UC Berkeley in 2000. After that, he spent 2 years at Microsoft Research, and then was recruited to our faculty here at Caltech, where he's now a professor of computer science. The field that Chris works in, and that he'll tell us something about tonight, is called the theory of computing. This is a fairly young field. It's about half a century old. And it's sort of at once a field of mathematics and also a field within engineering in some sense. And in this field, we start out with really any computational problem, even very mundane ones. For example, what's the shortest way to get from point A to point B on a map? Or what's the fastest way to multiply two integers? Or if you want to flip that around, you could say, if someone gives me an integer, how can I find its prime factors? Problems like that are sort of our starting point. And we study sort of in depth really just how efficiently you can solve these problems. We like to give algorithms that do well, or we like to show maybe that you can't. And at some level, all of you have been affected by the answers to some of these questions. So if you've ever used, computer-generated directions, for example, maybe you switched on one of the popular apps as you drove over here tonight, you've been affected by the solution given by theoretical computer scientists to the first type of question. And if you've ever made a financial transaction online, then the security of that transaction has depended upon the answers to questions like the last question I asked, having to do with factoring integers. So those are some examples. The scope of the field of theory of computing is really much vaster. It tries to quantify not only the complexity of particular problems, but to really build a theory around it and to bring some order to the overall picture of what problems are easy or hard to compute and to really quantify this. In the early days of the field, the methods were fairly elementary. That doesn't mean the papers were necessarily easy, but the methods were elementary and used only a smattering of mathematical tools. That has changed. And nowadays, really deep connections are being forged between the theory of computing and other branches of mathematics. Chris began his career really as a complexity theorist, more really just from the computer science side. And as his career went along, he became, though, one of the leaders in forging very strong connections between the theory of computing and the mathematical field of algebra. Let me just mention in brief two of his most notable contributions in this vein, as many others. In 2003, with Henry Cohen, he introduced a very deep approach to studying the complexity of matrix multiplication. And he's going to tell us a little bit about that tonight. And in 2008, with Kiran Kidlaya, he devised the fastest known algorithm for factoring univariate polynomials. That may sound a little bit like factoring integers that I mentioned earlier, and in some ways it is, but in fact the situation is very different, and that difference is precisely the kind of contrast that we have to study in this field, and it's the kind of difference that, when we learn about that difference, that's the kind of insight that computer science brings back to algebra. For these works and his many other great contributions, Chris has won an NSF Career Award, an Alfred P. Sloan Research Fellowship, and a Simons Foundation Investigator Award. Apart from his research, which doesn't guarantee he's able to stand in front of a crowd and utter a coherent sentence, he is also a very fine speaker, and in fact, the winner of an ASCII Teaching Award here at Caltech. So, ladies and gentlemen, let's please welcome Chris Umans, who will tell us about algorithmic magic behind the scenes of modern computer science.
Okay. So thank you. Thank you for the introduction, and thanks to all of you for coming out tonight. In today's talk, I want to tell you a little bit about how algorithms affect our lives, the role they play in our lives, and where they come from, how people invent them, how they devise them, and the ideas that go into that a little bit. So what is an algorithm? It's a recipe, a sequence of steps for solving a problem, for completing a task. And if you think about it, we all execute algorithms in our daily lives. Say every morning when you get up for work and go to work, you get up and you follow a sequence of instructions. You brush your teeth, you make the bed, you start the coffee brewing so that it's done before you get out of the shower, you take the shower, get your clothes on, the shoes, etc. And for those of us who are parents of young children, we execute a much more complicated algorithm. It involves sometimes loops, like please put on your shoes, I'm going to, please put on your shoes, I'm going to, etc. Okay, but the thing about computer algorithms that distinguishes them a little bit from the kinds of algorithms that I was just describing is that we usually want to think about a very general method or a general recipe that solves the problem no matter what. So instead of just figuring out how I'm going to get out the door in the morning, I might think about solving the problem by computer of given a bunch of tasks with maybe precedence constraints that say you have to complete this one before that one, and this one takes this certain amount of time, and that one takes that amount of time. Find the schedule by which I should do those tasks so I'll get out the door in the fastest amount of time. And that suddenly becomes something that we think of as a computer algorithm, or something that we can approach from the field of algorithms. And the other thing that distinguishes computer algorithms is we typically think of them as being applied to problems that are really huge, that are very large size. And that's what computers excel at. And so we want methods that work for very large size problems. Now, what makes a good algorithm? In the mathematical field of algorithms, we have a sort of a formal answer for this, but a good algorithm is a shortcut. It's sometimes a clever trick. It's something that you wouldn't have thought of, a way of solving a problem that is maybe not obvious. And then most importantly, it's something that's fast. That's the thing that we usually desire for our algorithms. And it avoids this situation, which some of us have encountered. It usually leads to swearing at the screen. So we want fast algorithms. We want our computers to be able to solve these problems quickly. We don't want to do this. And don't worry, I can stop this slide anytime. Okay, so I wanted to try to illustrate a point, which is that algorithms are really the core or the heart of lots of applications, the ones that we encounter every day when we interact with computers. And I thought of a smartphone as the best example of the interactions that many of us have with computers. There's often one in our pocket, and we can do all sorts of things. There's all kinds of apps, and I want to go through just a few of them and sort of illustrate the algorithm that lies at the core of the application in question. And Leonard mentioned a few of these. So if we think about a mapping application, it tells you where you are, but more importantly, if you say you want to get from point A to point B, it gives you the shortest path to get there, perhaps incorporating traffic and whether you want to travel on highways or on surface streets, et cetera, et cetera. But the algorithmic question that we would pose that lies behind this application is illustrated here. We have a network where we have individual nodes or circles that represent the locations or cities. We have links between them with numbers that indicate perhaps how long it takes to travel along that road from one place to the next. And then the problem is to find the shortest path between 2 points A and some other point B. And this is a problem we have a very fast algorithm for. And because we have a fast algorithm, we have these kinds of mapping applications. If this was a problem which didn't have a fast algorithm, we wouldn't be able to use our phones to, in a few seconds, tell us the best way to get across town or the best way to get to LAX in traffic. Here's another one. So YouTube, we often all have watched videos on YouTube or other streaming video services. And in this case, there's just not enough capacity on the channel that's to your phone or to your other devices to actually transmit all the information in all of the frames to see 60 frames a second of video. The only way we're able to do that is because we have data compression algorithms that work well, that are fast, and we have error-correcting codes and with fast algorithms to encode and decode information that makes it robust to the errors that happen as it's being transmitted. And so if we didn't have fast algorithms for these problems, we wouldn't have the video streaming that we rely on and we all enjoy on our phones or computers or other devices. Here's another one. So Google search. So Google search is a pretty amazing feature that you can, amazing application. You can type in a few words and search instantly, in a few milliseconds, get the answer to the most relevant web pages out of hundreds of billions. Okay, and there are a lot of algorithms that go on behind the scenes here. Many of them have to do with maintaining the, implementing this search on the infrastructure of many hundreds of thousands of machines and data warehouses and so on. That's sort of more inside computer science. But one of the things that made Google so successful when it started was, and still successful today, is that its search is really good at picking out the relevant results, the most important pages. And they use something they call PageRank. But underlying that is an algorithm. And that algorithm is something that assigns values to web pages, which are indicated with these little pages. And those values are essentially the probability that a random web surfer would reach that page. Okay? And somehow that gives a good proxy for how important that page is or how relevant that page is. Now, to compute that on an enormous corpus of web pages is potentially something that's hard to do, but in fact we have fast algorithms that give good estimates to those probabilities rapidly. And because there are fast algorithms to do that, we have really amazing search capabilities. Okay, so this is another instance where algorithms really are at the heart of an application that we all rely on. Here's another one. So Shazam and other services like it, other apps like it, will listen to a little snippet of the song that's playing on the radio and tell you what song it is, and then, of course, offer you the opportunity to buy that. And so what happens here is that the snippet of audio that you hear is encoded is recorded as some string of zeros and ones in digital form. And then we want to find a match between that and where it occurs in a list of the, say, digitally encoded list of songs that you're comparing it to. And you want to do that rapidly. Okay, so there it is there. And this is a problem that we would call string matching, and we have fast algorithms for it. And if we didn't have fast algorithms for it, we wouldn't have this application that we all enjoy. Now, if I change the letters, symbols from zeros and ones to A's, G's, C's, and T's, it suggests another application with the same algorithm. So here we have a small sequence of A's, G's, C's, and T's. That should make you think of genes, of DNA. These are the base pairs of DNA, the 4 letters. And we're interested in finding the occurrences of this in a large list that perhaps is a list of the genomes of some collection of individuals or a bunch of different species. So string matching again. And I put this up here to make a point about algorithms, which is that when we study algorithms from the theoretical computer science perspective, we want to think of problems that are expressed in such a way that they transcend application area. So solving the string matching problem lets you implement something like Shazam that picks the songs off the radio, as well as doing applications in bioinformatics. And then something that's a little bit more, that is more mundane, calculator application. And I'd like to just use this as a little bit of an example that we'll follow through for a few slides. So, okay, calculators existed a long time before they were always on phones. And they're very good at multiplying and adding really long numbers and doing that very rapidly. Okay? That's a really simple thing, but it gives a chance to think about algorithms that we're all familiar with. So let's just start with something which is very simple, which is just adding 2 numbers, really long numbers. Okay? And we know how to add 2 n-digit numbers using a number of operations, which is essentially proportional to the number of digits. Right? You have to go through each digit and add it up, and sometimes you have to add a carry in, but that's 2 or 3 additions for each column, and you go down the line and then you're done. Okay, so a number of steps that's proportional to the number of digits. That's good. That's a good algorithm, and it's a simple problem. Okay, what about multiplying 2 numbers? So we all know how to do this. If you're a 7-year-old who's encountering this for the first time, sometimes you might think, well, what I should do is I should just repeat the addition many times. I should repeatedly add this number to itself 1,426,000,000, et cetera, times. That's not a very good algorithm. That's an algorithm that will take a number of steps proportional to the magnitude of the second number times the number of digits, okay? And you would be waiting for a long time for your calculator to finish this calculation, okay? But you know a better algorithm, and you're taught it, everybody's taught it in 3rd or 4th grade. You should do grade school multiplication. And the number of steps of this algorithm is proportional to the number of digits times the number of digits, roughly, because, well, we know how to do this. We first multiply this number times each of these digits. We get this number. Then we multiply the next number of the second line times the first. Get this, and then we add them. And since every digit here got multiplied by each of the digits here, once the number of basic operations is roughly the number of digits of the first number times the number of digits of the second number. Okay. And by the way, the fact that there's a nice easy algorithm for this is the reason that people learn this in school. And the fact that there's a quadratic formula that gives you an algorithm, if you think of it, for solving quadratic equations is the reason you learn that in school. And the reason, you don't learn some other things because there aren't fast algorithms. Like quintic equations. So if we think about multiplication of two numbers, we have two methods. We have a grade school method, which takes a number of steps, which is about the number of digits squared. And a computer scientist would ask the following question, which is a good question: can this number of steps be improved to about the number of digits? And in fact, even for this very simple problem, we don't know the answer to this question. We do know a method that's much better than grade school multiplication, that gets close to the number of digits, but not that exactly. And we really don't know if there's a simple algorithm or even a complicated algorithm lurking out there that actually gets to the number of digits. So this is the figure of merit when you talk about comparing algorithms. You're looking at how many steps they take as a function of the size of the input, and that lets you really consider algorithms that work well for larger, very large problem sizes. Okay, so where do these come from? How do people come up with algorithms? So what does algorithms research look like? So we don't do experiments. We also don't have fancy equipment. We don't even need to use large computers, or we don't tend to use large computers. An algorithms research lab, if there is one, looks much more like this. A pen and paper, a lot of math, sometimes there's a couch, some coffee. Okay, so what sorts of ideas and why is there so much math? So let me, we're going to sort of take an example of computing connectivity and follow that through as we sort of find the problem that's underlying this, try to solve that problem, and I'll give you a sense of some of the ideas that really actually approach the cutting edge of research in this area. So connectivity. So we start with a problem that's, again, a familiar one. There's a map of the freeways in Los Angeles. Some of them are red, indicating there's a lot of traffic. Some of them are green. We want to head on those. And a question we might be interested in answering is which locations, which I've marked with the red dots, are reachable from which others while avoiding traffic. So you can travel only on the green routes, and the red ones are not allowed. Okay, so which ones are reachable from which others while only traveling on the green roads? Now, before I tell you how we're actually going to try to solve this, let me just remark that this question about which things are connected to which other things in a network is something that arises in a lot of applications. So here's a picture of a gigantic network. It's a fragment of the web graph. Each of the dots here represents a web page, and the links indicate which web pages have links one to the other. And you're potentially interested in different applications in computing connectivity in a graph like this. But you might also be interested in computing connectivity in a network that actually is a network of computers, to know which two computers can actually reach one another through a sequence of links, which ones can transmit information to which others. Networks of financial transactions, maybe you have nodes that represent individuals. You have links that indicate whether they've transferred a large amount of money, and telling which individuals are linked to which others might tell you something about financial fraud or money laundering. Social networks, you're interested if your network represents individuals and friend relationships. You might be interested in who's connected to which other person by a sequence of steps. Protein interaction networks, an application from biology. You might be interested in which protein can affect which other portions of the interaction network and which ones are sort of separate. So this connectivity problem arises in a lot of applications. And now I would like to tell you how we sort of go about solving it. So the first thing is, how do you record the information that sort of expresses the problem? So we have these nodes and we have links between them. And I'm going to suggest that we organize it in a matrix like this. So we have, in this little example, 4 locations that label the rows, 4 locations that label the columns. And we're going to put a 1 in a given entry to indicate that you can get from the location labeling the row to the location labeling the column, okay, and a 0 if you can't. Okay, so for example, this 1 indicates you can get from location 1 to location 3. Okay, and up here is up in the corner, there is a little picture of the network that's expressed in this little example. Okay, so we're going to store information in the network, and what this in a matrix, excuse me. And what this matrix tells you is where you can get in at most 1 hop by following at most 1 link. Okay, that's sort of the starting point. And now, what if we want to know from this where you can get to in at most 2 steps, following at most 2 links? Where can you get in most 2 hops? So one way to figure this out is to write another copy of this matrix, which indicates what you can get to in 1 hop, and start filling things in. So so here I'm going to ask the question whether we can get from location 2 to location 3 in at most 2 hops. And I claim that you can figure that out by figuring out where you go in the middle. If you're going to go there in 2 steps, you have to go somewhere in the middle. So you either go from 2 to 1, and then from 1 to 3. Okay, but that's not possible because we have a 0 here indicating you can't get from 2 to 1. Or you go through a midpoint, which is 2. So you go from 2 to 2, and then from 2 to 3. And that's also not possible because there's a 0 over here indicating you can't get from 2 to 3. And then you check whether you can get through via a midpoint of location 3 and whether you can get through with a midpoint of location 4. And in this case, the answer is 0 because there was no way to get there. There was no midpoint that you could pass through on the way. And this information was contained in this row here and this column. Those were the entries that I looked at in computing what this 0 was over here. And in fact, if you think about what I did, I took in a given entry here, multiplied by a corresponding value here, and then added those up as I went across the row and down the column. Okay, and then here's another one we might want to compute. Can you get from 3 to 4? And if we do the same process, we say there has to be a midpoint. We can look and say, well, if you go from 3 to 1, and then from 1 to 4, we actually can do that. We can get from 3 to 1 and from 1 to 4, so we can get from 3 to 4. And then we look at the other possible midpoints. You can't do it with midpoint 2. You can do it with a midpoint of 3, and you can do it with a midpoint of 4. And so we can actually put a 3 there that indicates not only can you get there, but there's 3 different ways you can get there through the midpoints. Okay? And don't worry, that's the last one I'm going to do in all of its detail. Okay? But we can fill in the whole matrix in this way. That's why we need algorithms, so we don't have to do all this by hand. We can fill in the whole matrix this way. And it turns out that the operation that we just did is the matrix multiplication. It's the product of 2 matrices, and some of you know this. Okay. Now, if we can do that to compute where you can get to in 2 hops, we can take the 2-hop matrix and repeat the same process to figure out where you can get in at most 4 hops. And then take the 4-hop matrix and figure out where you can get to in at most 8 hops, each time doubling. And it doesn't take many doublings, only logarithmically many, before you figured out where you can get to in n hops, where n is the total number of locations in the entire network. And that solves the problem. Okay? So in order to solve this problem, we've discovered we need to figure out how to do this process of multiplying matrices. And not only is matrix multiplication important if you're trying to solve connectivity, but it turns out that it's a fundamental task for a lot of other reasons. Almost all the basic operations on matrices, if you know something about linear algebra, can be performed via matrix multiplication. So these are things like inverting a matrix, computing its determinant, computing various decompositions of matrices, solving systems of linear equations. Okay, so all of these things, which are basic problems you might want to solve in other settings, can be performed via matrix multiplication. And it's used in other settings. Often it's the bottleneck in how fast you can solve those problems. connectivity is but one example. Okay, so this is an important problem. Let me just give you a few of the list of applications of matrix multiplication and some of these related problems just to give you a sense of how widespread its use is. It can be used in certain kinds of economic optimization. It is used in simulations of all types where you're simulating some sort of physical system, say, for example, climate modeling. Finding roots on maps, it's like the example that we've been talking about. Cracking crypto systems. The last step of these is often involves solving a very large system of linear equations, and you want to do that fast. Matrix multiplication is related to that. Okay? And in this era of big data, we have huge matrices to work with. Okay? Now let me just give you one concrete example, because it's kind of an interesting one. So there's this problem called topic modeling that people are interested in doing that it also involves a matrix multiplication-like task. And here, the object is to take a corpus of information of web pages, like, for example, the set of all the New York Times articles for the last few years, and automatically identify some of the dominant topics that occur without knowing in advance that you might categorize things into sports and politics and arts and things like that. And one way to do this automatically is to record the information about which words occur on which web pages. So I labeled the rows with the web pages, I label the columns with the different words, and then a given entry tells you how many times a given word appears on a given web page. And it turns out that one way of solving this kind of a problem is to decompose this matrix using one of those decompositions that's related to matrix multiplication, and that automatically tells you where what the dominant topics are and allows you to categorize new web pages according to that. And I mentioned this example just to give you an illustration of an instance where the matrices are huge. Okay? The number of rows here is something like the number of web pages. It might be on the order of hundreds of thousands for a problem you're interested in. The number of words is similarly large, and somehow you need to be able to operate in a fast manner with fast algorithms on these. Okay. So how do you multiply matrices? How fast can you do this operation? So we see that it's at the core of a lot of applications. So we're going to count the number of additions and multiplications as our basic operations as we try to do this. And what's the first thing that we know? We saw how to multiply matrices with, of size n by n with about n cubed operations. That was the process that we started to go through when you got tired of me going entry by entry. If you can see that the result matrix, the one on the right here, has n squared entries, each of which involves information from a row and a column, which had about n entries each. So there's about n operations to combine those, and n squared result entries. N times n squared is n cubed. Okay, so that's sort of the basic way of doing this. And the question, again, the computer scientists ask is, can we do better? In fact, we might even be so ambitious as to try to get close to n squared. That's the number of entries in what you have to write down. And maybe you could get to a sort of an amazing algorithm that gets close to that. And in fact, experts who have thought about this problem suspect that the answer to this is yes, we can actually get something close to n squared. But nobody knows how to do this. This is regarded as one of the most prominent unanswered questions in algorithms. Can you multiply in almost n squared operations? Now in 1969, before 1969, people actually started to think maybe the n cubed algorithm that we just discussed was the best possible. And it sounds natural. Like each time you start to compute a new entry, it looks like you're taking fresh values. So how can you really save over the n cubed operations that we just sort of went through? Volcker-Strassen in 1969 showed that you can actually do a lot better. You can do something like n to the 2.81 operations. And never mind what the 2.81, where that comes from. But it's better than n cubed, significantly better. And at the time, it was really shocking. It still sort of is. And I'm going to show you how you do that. And it's going to look a little bit like a magic trick. In fact, even to students in algorithms courses, it often looks a little bit like a magic trick. To give you a sense of where that magic comes from and how that could actually be, I want to first devote one slide to a magic trick for numbers that's similar. Okay, so this is actually something that you can do, either in your head or if you have a pen and paper, you can jot something down. Okay, so I want you to, in your head, pick a two-digit number. Okay? And now, exchange the two digits and subtract the smaller of those numbers from the larger one. Okay? That's the hardest step. Okay, got it? So remember that number that you've got. Now, take the result and exchange the two digits. If you need to put a leading zero, you can. Okay? And add that to the result of step 3, the subtraction step. Okay? You done? Okay? Okay, so, and I'm sorry to say that if you didn't get 99, you made the mistake, not me. Okay. So why, some of you have seen something like this before. So why does this work? Well, you can figure out why it works. You can write down some equations involving, simple equations involving the two digits you start with. You realize that there's an identity here. There's two ways to get to the same result. One is to just say 99, and the other is to follow the sequence of steps that I described to you, and you'll get to 99 as well. So there's two different ways to get to the same place. And in fact, what Straussen's algorithm for matrix multiplication does is a little bit of a magic trick like that, two different ways to get to the same place. So here is that magic trick. So here is 2 by 2 matrices. We're going to look at the simplest case. So 2 by 2 matrices, here are the different entries. These A's represent the numbers in the first matrix, B's in the second matrix, and then here are the results that you're supposed to compute. And you can see that this one, for example, if you remember, involves this row and this column, and we're supposed to take A11 times B11 plus A12 times B21, et cetera, and I wrote out all the things you're supposed to compute there. That's what you need to do to compute the product of these matrices. Now, here's Straussen's algorithm. I don't expect you to look at this in detail, but I'll just point out that that's actually the complete algorithm, by the way. It tells you that you should compute 7 different products that are called P1 through P7, each of them being the product of some numbers in the first matrix times some numbers in the second matrix. And then you take some sums and differences of those, and it turns out that those give you the 4 values that you wanted to put in this, that you wanted to find. Okay? Now, it actually looks like a more complicated way of doing things. There's more additions and subtractions and stuff that's going on here. So what's better about this? Well, it turns out that if you count the number of multiplications, over here there's 8. There's 1 here, 2, 3, 4, 5, 6, 7, 8, right? 2 for each entry. And over here, the number of multiplications is just 7. There's 7 here, P1 through P7. Okay. Now, some of you are looking at me like I must be crazy. Saving 1 multiplication doesn't seem significant. Okay, but the key idea is then to use this on giant matrices. So if I have an n by n matrix, that's huge. What I should do is break it up into 4 pieces and break the second one up into 4 pieces, each of which is a matrix of half the size. And it turns out that these equations still hold when you're talking about matrices instead of numbers. And then you use this strategy to multiply, and every time you have a multiplication of smaller matrices by another smaller matrix, you use the same strategy again. That's what's known as recursion, a very powerful idea in computer science. And if you analyze this algorithm, it turns out that that savings from 8 to 7 turns into a much more significant savings and gets you from n cubed operations down to this n to the 2.81. Now, you can say, well, that's not 2.81, it's kind of close to n cubed. Should I be even that impressed? And the point is that for large matrices, this really starts to matter. So for matrices of about 100,000 by 100,000, let's say, this gives you something that's something like 9 times faster, according to my little calculations. But the holy grail here is to find an algorithm that takes something like n squared operations, and the speed up over the simple algorithm would be something like 1,000 for 1,000 by 1,000 matrices. Okay. So that's what we'd like to find. Okay, so since 1969, there have been a lot of people who've worked on this, and they've made improvements over the years that involve a lot of different ideas. They've gotten this exponent down to the 2.37, but not the 2 that we hope for. And all of those ideas, from a certain perspective, can be thought of as like different magic tricks like this one that we just saw, okay, that work on larger and larger matrices. So now a question is, how do you come up with these magic tricks? Is it just somebody staring at a sheet of paper and thinking really hard and coming up with something like that? Because that doesn't seem possible, right? There has to be something more systematic or principled in this. And I'd like to tell you a little bit about a way of coming up with new magic tricks that we invented, which I hope may lead to an optimal algorithm. So this is an idea that Henry Cohn and I had for discovering new magic tricks. Now, to do this, I'm just going to describe the idea in a few slides. We have to think about going beyond numbers. So instead of multiplying the matrix entries by +1s and -1s and taking sums of them, we're going to do something which sounds crazy and almost nonsensical. We're going to involve the symmetries of a triangle. Okay, so what are the symmetries of a triangle? So here I have a triangle. And I can think of the different ways of rotating or reflecting that triangle so that it stays the same. Now, I put colors on the points of the triangle so you can follow what's happening. So here's the original triangle. And then I can rotate it 1/3 of the way that way. And it's still a triangle, right? Or I can rotate it 1/3 of the way around that way. Okay. And then I can also take each of these 3 rotated triangles and I can reflect them, keeping the red point the same and flipping the other 2. You can try to visualize that. And I'm going to signify the 6 different symmetries of a triangle. These are all of them, by the way, by these little symbols here. So 1 means don't do anything, then rotate that way, flip, flip, or flip. Okay, so there's 6 different symmetries of a triangle. Okay, now the cool thing about these objects is that you can multiply them in a certain sense. You can apply them one after the other. So for example, if I do a flip and then a rotate and then another flip, if you think about it for a little bit, you'll have rotated in the opposite direction. Okay. And so they form a mathematical object called the finite group, which is a very well-studied area of mathematics. Okay, so what does this have to do with matrix multiplication or algorithms? So here's a crazy thing that you can do. You can take this 2x2 problem again of trying to multiply matrices, and it turns out you can write down an equation involving the matrix entries you want to, you're given and the ones that you're trying to find that involves these symmetries of a triangle. This is actually an equation that holds, as written on the slide. And then, maybe more surprisingly, you can make sense of this equation. Okay? You can turn it into a magic trick in a very systematic way, like the ones that we saw before. And this uses an area of mathematics called representation theory. It's a well-developed area of mathematics. The savings comes from the size of that finite group that you use. Okay? So the task now becomes one that's mathematically appealing. We're interested in studying more complicated groups of symmetries and finding ones which support some kind of an identity or an equation like the one I wrote on the previous slide, which we can then sort of manufacture one of those magic tricks that leads to a faster algorithm for matrix multiplication. So using these ideas, we've gotten down to 2.41 in the exponent there, and what I believe is a clear potential path to n squared, but we'll see. So this gives you, I hope that gives you some sense of the ideas that get used and where mathematics comes into play. Okay, a question that I always get asked when I talk about this is, are these algorithms practical? And the answer is no, not yet. Okay, so the improvements in this case for these kinds of algorithms only start to kick in for astronomically large matrices. I don't even want to tell you how large. Okay, they're not things that you can actually expect to implement and benefit from yet. Okay, and this is a phenomenon that often happens in algorithms research, and it's not something that's to be so worried about. The algorithms as a field really helps you identify the sort of the crux of the problem, the barrier that you have to cross. And in this case, the barrier is getting close to n squared as a growth rate for how fast the algorithm can run as a function in the input. Once you get past that, then you can work on trying to make it practical. And so that's a common pattern in algorithms. So at this point, this question is more of a scientific question or a mathematical question. And if we can answer that, then we can move on to the engineering problem of trying to get really practical algorithms for this problem. Okay, so that's a bit about where algorithms arise in different applications, and an example of one that arises in connectivity, and ideas that get used for it, where mathematics comes into play. Now I'd like to say something about where our sort of imagination fails us, where we don't seem to have any good ideas for doing clever things, and these problems end up being the hard problems, sort of in our universe of problems. So to describe those, let me go back to this picture that we had before of a network of roads, of freeways in Los Angeles. And we can identify some cities that we might be interested in with the red dots. And of course, as computer scientists, we do the process of abstracting from the actual data to some more abstract problem. So we're going to delete the map and just keep these links between the cities. And we, of course, indicate maybe lengths, numbers on them that indicate lengths, something like that. Okay. And a question we would be interested in asking, if we're doing the mapping application that we talked about at the beginning, is what's a shortest path between point A and point B in this network? Okay? And there are fast algorithms for that. That's what I asserted at the beginning. Leonard mentioned something about that in the introduction. There are fast algorithms for finding the shortest path between 2 points, and this is how we have mapping applications that work well. So we can find a path like this. Now, what if I change the question just a little bit to ask about finding the shortest tour between 2 points? So this is something that starts at A, ends at B, but you have to visit everything in between in some order exactly once. So this is like the problem of I want to travel from LA to San Francisco, and I want to make sure to hit all the national parks along the way, something like that. And this is another problem that you can ask for an algorithm for. The best algorithm that we know for this problem, even though it seems a little bit like the problem of finding shortest paths, is a really stupid algorithm. It's the one that sort of essentially tries every possible path, every possible ordering. It's the brute force, exhaustive search way of solving this, and it's bad news. You don't want to do things that way. I mean, having to do exhaustive search or brute force is almost like having no algorithm at all. And why? Because if you have only n locations, you need to check something like n factorial different tours if you're going through all of them. And now n factorial is like n times n minus 1 times n minus 2, et cetera. That's a huge number. Just as a little example, if there are only 100 sites, a computer that can try 1 billion tours a second would take billions of years to solve this problem, to try out all the tours. So this is like having no algorithm. Okay? When you have to resort to exhaustive search, it's like having no algorithm at all. So that's a hard problem. And here's something that's a little depressing. Okay? For many, many problems that we can pose or write down that are within the scope of the sorts of things we'd like to solve by computer, exhaustive search, or essentially exhaustive search, brute force, is the best that we know how to do. We don't have any clever ideas or shortcuts for these problems. And as I said, solving problems by exhaustive search is, prohibitive. So it's really like not solving the problem at all, or not having an algorithm for the problem at all. And from this perspective, the problems that are solvable by fast algorithms are more of the exception than they are the rule. Each time we have a problem that we can solve with a fast algorithm, there are all sorts of cool applications that arise from that. But there are sort of most of the problems are actually ones where we just don't have ideas. Exhaustive search is the best. So if we think of the universe of problems, here are the problems, many of which we've discussed: integer addition and multiplication, matrix multiplication, connectivity, string matching, shortest path is the sort of thing that you need to do for map applications, convex optimization, a big class of problems that you might be able to solve. These are problems that we actually have fast algorithms for. There's a whole bunch of other problems where basically the best thing we know how to do is to just try everything: exhaustive search, brute force. This includes cracking cryptosystems, which is good news, factoring integers, but things like protein folding, computing how a protein folds, shortest tour that we just discussed, facility location, optimal scheduling, and then I don't have enough room to sort of indicate there are thousands of problems arising in every application area, from AI to economics to physics to biology, optimization, network science, all sorts of areas. And over the years, people have identified all of these problems that they'd like to solve They sort of write down in a nice abstract form that we like to pose them in, and then it turns out that as far as we know, exhaustive search seems to be the best. And now there's something that's really incredible that's true about all of these hard problems, or many of these hard problems. A huge number of them are actually the same problem. So there's ways to transform one into the other and the other into the one in a fast way, so that if you can solve one, you can solve the other. That's a huge and very important realization, hugely important and very impactful realization, that these are all the same problem in different guises. So people who had thought about and worked on these problems from all sorts of different application areas were really trying to solve the same problem. And perhaps more importantly, if you can find a fast algorithm for any one of those, any one, then you automatically get a fast algorithm for all exhaustive search problems. Any one, even ones that we didn't include in our list. And that's amazing. So these problems up here that have that special feature are called NP-complete problems, is a technical term. And the problems down here that have fast algorithms are called P problems, and the ones that basically allow exhaustive search are called NP problems. And this is a big question in computer science, whether there exists fast algorithms, for the NP-complete problems. Now, one of the major implications for having a fast algorithm for exhaustive search problems would be breaking cryptography, and one of the ones that people often think about. So cryptography is something that is susceptible to exhaustive search, right? You can try all the passwords, try all the keys. And if you had this sort of magical fast algorithm that could solve exhaustive search problems, among many other consequences, you'd be able to break cryptography. It would essentially render cryptography useless. Security on the internet would be non-existent. So this is a hugely important question. Now, don't worry too much. We don't think NP-complete problems have fast algorithms, okay? We don't think so. This is based on the fact that there are lots of problems that people have effectively been trying in lots of different application domains that are NP-complete problems, and nobody's been able to come up with any clever algorithm for them, okay? And there's some sort of philosophical reasons why we think this should be impossible, but we don't know how to prove this. And there's one point I want to make, which is that everything that I've talked about exists in the domain of mathematics. They're questions that we can, in principle, hope to resolve definitively one way or the other. And if we can't find a fast algorithm, if it's impossible to find a fast algorithm, we ought to be able to prove it in a mathematically rigorous sense. And we don't know how to do that. We don't have the ideas that will let us prove that, if that's in fact the truth. So we're in this state where we don't know what the truth is, although we have a strong belief that you can't have fast algorithms for these problems. So this is called the P versus NP problem. Some of you may have heard of it. It's one of the millennium problems. It was identified as one of the most important problems in mathematics. Back in 2000, there's $1 million prize for resolving it one way or the other. And I think you can probably see why. It's really consequential. Now, because Robert Redford and Dan Aykroyd can convey the drama of this possibility probably better than I can, I want to show you this short clip from a movie called Sneakers from a number of years ago, which is a fun movie. It's about 4 investigators who are searching for this black box that is sought after by the NSA and foreign governments. And in this scene, they're figuring out what the black box does. Why is it so important? But every computer scientist who saw this movie said, aha, the black box has a fast algorithm for an NP-complete problem inside of it, because, well, you'll see watch for Robert Redford to say it's not a code breaker, it's the code breaker at the end of the clip.
Fish, I think you better come over here. You should go back there. Yes. You're going to do something impossible next. What about this? Federal Reserve Transfer call at the Virginia. 90 billion a day over there. Okay. Let's do it. It's encrypted. Kate? Oh, thanks. This point. Everybody want to check out Federal Reserve? Okay. Hey, no, screw around with that thing. How about that? Yes, however. Okay. There we go. Rolling. Unbelievable. Anybody want to back out and anywhere? All right, what else? Air traffic control system. Okay, mother.
Oh my God.
Oh, this is awesome. Cryptography systems are based on mathematical problems so complex they cannot be solved without a key.
Janet must have figured out a way to solve those problems without the key, and he hardwired it into that chip.
Maybe we want to crash that. Turn it off. Turn it off. So what's the code breaker? No. It's the code. No worries. Honey, you and Melissa get your thing.
Okay. I hope you like that. And if you like that, you should watch the movie. It's a fun movie. Okay, sneakers. So that's actually where I wanted to leave off. I want to just say a few words about what I tried to convey today. So in this era of computation and big data, fast algorithms are really the things that enable applications. And we saw a bunch of examples of that. I hope I convinced you of that. There are really fundamental and basic algorithmic questions that are yet to be answered. The question about the matrix, optimal algorithms for matrix multiplication, even the question about just multiplying numbers, which sounds like something that should have been settled a long time ago, is not known, as we discussed. Fast algorithms can be found via clever ideas that sometimes look like magic, but often have their basis in mathematics. And then this part that was very dramatically portrayed in the movie clip, a fast algorithm for any one of the thousands of NP-complete problems would yield fast algorithms for all exhaustive search problems. And one consequence of that would be breaking all cryptography, and of course there would be many other consequences as well. And that's something that we don't know if that's true or not. We suspect that it's not, so you shouldn't worry too much, okay? But we don't know how to rule it out. And so it's sort of this mystery at the core of computer science and the core of algorithms that maybe there's a clever idea that will suddenly enable us to solve all these problems via fast algorithms, and we don't know. So it's this kind of mystery that makes the field really fascinating, and I hope you've enjoyed learning a little bit about it tonight. Thank you.